Take away the infrastructure, the supply chains, and the economy, and the Earth is strictly a collection of physical elements: wind moving through a canyon, minerals embedded in rock, and carbon bound in forests. We tend to look at these raw materials and instinctively label them as resources. But in their natural, untouched state, these physical elements are economically and functionally neutral. A vein of copper or a flowing river possesses no inherent utility on its own. Nature provides the bounty, but that bounty only undergoes a state change into a valuable asset when human intellect, labor, and technology are applied to extract and transform it. Because of this dependency, human capital is the strict required prerequisite for natural capital to exist in any functional sense. To understand how global economics actually operate, we have to systematically map the complex chain of state changes that turn neutral matter into human utility. We can construct this map by building an ontological tree from first principles, establishing our planetary baseline, and categorizing everything that grows from it. This classification must be rigidly bound by physical limits. The primary boundary is temporal availability, the speed at which a material exists relative to human lifespans. The secondary boundary is material entropy. We have to categorize elements based on their physical mutability, tracking what happens to their atomic structure upon use. By mapping the absolute physical boundaries of nature alongside the human systems designed to exploit them, the actual mechanics of global wealth become entirely visible. Building this taxonomy requires establishing our foundational node, human beings. Since humans are the mandatory lens through which neutral matter is filtered, they are the base from which all economic utility originates. This diagram illustrates the human framework, dividing our foundation into two sectors: demographics and institutions. The demographics branch begins with quantity, representing the sheer demographic size of a population and its total available workforce. But sheer headcount is limited without the second metric, quality. Quality measures the literacy, health, and technological expertise of that population. A highly skilled population dramatically scales a nation's capacity to process complex natural elements. The second major branch of this human foundation covers structures and institutions. Structures represent the physical manifestations of human organization. These are the factories, roads, and schools constructed to physically distribute and process resources. Institutions are the societal organizations, governments, research bodies, and educational systems that dictate how effectively those structures are managed. A high-quality population operating within robust, efficient institutions provides the mandatory filter required to convert the Earth's raw materials into functioning assets. Moving outward from human frameworks, we encounter the external physical world. Here, we classify natural resources, strictly defined as gifts of nature that exist completely independent of any human intervention. To categorize external materials, this chart maps them against a time-constant axis, using chronological availability as the primary dividing line. We establish this divide by measuring a mathematical ratio, the time it naturally takes a material to form, divided by the speed humans consume it. This temporal ratio gives us our first distinct natural category, renewable resources. A resource is classified as renewable if it can replenish itself through physical, chemical, or mechanical processes within a short, human-relevant timescale. Conversely, materials that fail this ratio fall into the opposing taxonomic category, non-renewable resources. Non-renewable formation requires millions of years. Their replenishment rate is virtually zero when measured against the speed of human extraction. Because of this extreme temporal mismatch, non-renewables carry the strict physical constraint of permanent exhaustion. Once consumed, they cannot be replaced on any timescale that matters to a human economy. If we zoom in on the specific mechanics of the renewable branch, we find two distinct operational models. The first subcategory is classified as continuous or flow resources. Flow resources are defined by their kinetic permanence. They are constantly available, and the act of a human consuming them does not diminish the supply. Tapping into wind energy, harnessing solar radiation, or routing water through a turbine leaves the total volume exactly as it was. The second subcategory operates on a much tighter margin, biological resources. These are the living components of the environment. Unlike kinetic flow, biological supplies are entirely dependent on active reproduction to sustain their numbers. We subdivide this biological branch first into natural vegetation. Plant communities, such as naturally growing forests, serve distinct functional roles. They grow without human aid, providing raw timber, generating oxygen, and maintaining local ecological balance. The final component of the biological branch is wildlife. Animal species living in their natural habitats provide the biological mechanics required to maintain the food chain and secure overall environmental biodiversity. While flow resources offer infinite kinetic energy, biological renewables are fragile, push human consumption past the rate of biological reproduction, and the cycle breaks permanently. Returning to the non-renewable side of the tree, we hit a different set of absolute limitations. Here, the boundary isn't time. It is thermodynamics. The classification depends entirely on how the material behaves structurally after its first human use. This chart divides the non-renewable node based on structural integrity, starting with recyclable resources. A recyclable resource is defined as a material that does not lose its intrinsic structural value after use. Metals like iron, copper, and aluminum can be melted down, processed, and deployed repeatedly without degrading the base element. The exact opposing path is the thermodynamic dead end, non-recyclable resources. These materials are completely consumed or transformed irreversibly upon use. They cannot be recovered, captured, or recreated. Fossil fuels, like coal, crude petroleum, and natural gas, are the absolute prime examples of this one-way material destruction. The physical state change is absolute. Upon combustion, the solid or liquid fuel turns permanently into ash and exhaust gases, instantly exiting the economic supply chain. Non-recyclables are a straight line of material entropy. Once ignited, they are permanently deleted from both the Earth and our taxonomic framework. Looking at this completed matrix, we have an ontological map of global utility, built entirely from first principles. The right side illustrates the strict physical boundaries of the planet. Deep geological time and absolute thermodynamic mutability dictate exactly what natural matter is available. The left side establishes the human boundaries. Despite the hard physics of nature, the actual economic utility of that matter is governed by human demographics and institutions. When we map the systemic dependencies across the diagram, the extraction of every natural element links back to human capability. The quantity and quality of the population acts as the master bottleneck for the entire planetary system. A static, chemically neutral planet cannot generate wealth, utility, or civilization on its own. Because processing natural elements requires complex observation, extraction, and management, a highly skilled human population remains the irreplaceable variable in resource economics. The true definition of a resource is simply human intellect successfully applied to the raw, neutral material of Earth.